everybody, this video is going to be a brief introduction to the topic of thermochemistry. Some of the things talked about may seem like common sense, but sometimes it helps to just hear them in a more official way with more science language. Even though you may experience them in real life, it may be helpful to see it from the chemistry perspective. People have a tendency in this chapter to focus on the math and they forget to study the concepts. And then they get some of the questions wrong that are based more on the conceptual pieces. So make sure you pay attention to this lesson because those things are still important. We may not practice them as often as we practice the math, but that doesn't mean they're not important. Okay, so let's get started. So thermochemistry is the study of energy transfer in the form of heat when we're doing a chemical or a physical chemical reaction or physical change. So the problems that we are going to have are going to talk about energy and temperature and the heat. Those are all things that you'll hear in this chapter. One thing that you need to be a little bit careful about is that you cannot use the terms energy, temperature, and heat interchangeably. They do mean slightly different things. I understand that in real life we may use them that way, right? Interchange them, but they're not the same thing, okay? And so please be a little bit careful. I think sometimes while our real life experiences help us on this chapter, they can also cause a little bit of a problem. You have to be a little bit more specific. So energy is a pretty generic term. If you want an official definition, it's the ability to do work, which means that an object has been moved. Okay, it's a very physics type of a definition. There's two types of energy. We could have energy that is stored due to the position. Imagine if you climb really high up on a ladder. If you fall off, it's going to hurt a lot more if you're up high versus down low, right? You have a lot more potential energy the higher you get when you're climbing up that ladder. In chemistry, the potential energy is stored in the composition. So in the bonds, in the molecules, things like that, okay? Kinetic energy is energy due to motion. When you're in the process of falling off that ladder, your potential energy is turning into the kinetic, right? Instead of stored energy, you're moving, and so it's the kinetic energy. The first law of thermodynamics is basically the same as the law that we're used to, the conservation of mass, right? We're not going to create or destroy it out of thin air. It is not magic. If one object loses energy, something else has to gain it. It has to go somewhere. It's either going to go to a different object or it's going to go into the surroundings, okay, or vice versa. One thing that sometimes comes up is people asking, well, how are these two things so similar? Why are they basically the same? And it's because these laws are connected through the fact that energy and mass themselves are related. So you've probably heard of the equation E equals mc squared. It's a pretty simple looking equation. Obviously, it was a big deal for Einstein to come up with it. It's a pretty complicated concept, but it's a pretty simple equation. And what it tells us is that energy and mass are basically different forms of each other. We can convert back and forth. We can't destroy either of them, but when we're doing things like nuclear reactions, we can definitely convert back and forth. So that's why those two laws are so similar. Two more words that tend to get misused are temperature and heat. Temperature is a measure of the molecular movement. How much are those atoms moving, okay? Heat is a little bit different. It's talking about the energy that is available to be transferred due to the movement. So that's going to take into account not just the movement, but also the quantity and type of molecules. So it's the difference between saying the molecules are moving really fast and the molecules are moving really fast and you have a whole lot of them, okay? One molecule moving quickly won't have a lot of heat to transfer. A whole bunch of them will have a lot of heat to transfer. So they're related, but they're not the same. I like this example. I think this helps kind of get it into your brain what the difference is. Which would hurt more, a tablespoon of boiling water being poured on you or an entire pot of boiling water being poured on you? Even though they have the same temperature, they're boiling, so they're at 100 degrees. One of them is going to have a lot more heat present. There's a lot more heat energy that could do damage, right? So taking into account both of the movement and the quantity. Here's another example. If I were to ask which has more heat, we look and say, look, they have the same temperature. But this has way more molecules present, right? So this one would have way more heat. One more thing that tends to be a little bit tricky for people is thinking about the direction of heat flow. We are fairly self-centered creatures. We tend to perceive everything from our perspective. And that gets us into a bit of trouble when we talk about the direction of heat flow. So heat will always, always, always go from hot to cold. The fast-moving molecules are going to bonk into the cold ones and speed these ones up. We always think of it that way. The energy is flowing into the cold ones. When we do these problems, if you are not careful of the direction of your heat flow, you're going to get your plus and minus mathematical signs mixed up. We may in real life say, oh look, the ice cube is cooling my drink down. But technically the way we should phrase that is my drink is heating the ice up. We are warming the ice. We are never cooling anything down. We are always warming something up. Now, if you go around talking to people in real life saying, oh, look, my drink is heating up the ice cube, they're probably going to look at you weird, right? So this is a classic example where we need to be a little bit careful of which perspective we're having. Always think about heat going towards the colder object. When we have something that is endothermic, the reaction, the chemicals themselves, or the object, whatever it is we're dealing with, is absorbing heat. The heat is going into the object. The reason this is a problem for us perspective-wise is we are going to feel cold. If this object is absorbing heat, the heat has to come from the surroundings. So if my hand is out here in the surroundings, I'm going to feel cold. I can't stick a thermometer inside a chemical bond to see if it's getting energy absorbed. I can only stick my thermometer in the surroundings. So if the surroundings are losing energy because it's going into the object, into the system, I will feel cold. My thermometer will show the temperature getting lower because the object is absorbing heat. Since we are self-centered creatures, we feel cold and think things are being lost, but really the object is gaining the energy. Exothermic is the opposite. The system, the object or the reaction, the chemicals themselves are releasing heat. Heat is being released. And so we are going to feel hot because the energy is being released towards us. You see your thermometer go up and you think that, oh look, it's getting hotter, must be absorbing energy. But our system is not the thermometer. Our hand is not the system, right? We are interested in the object or the chemicals. which are losing the energy. Okay, so be a little bit careful about your perspective. I think reminding yourself that you can't stick a thermometer inside a chemical bond, you can only stick it in the surroundings, is helpful, because that kind of forces your brain to keep the right perspective. Okay, so that's the big deal. Little bit about temperature one more time. Temperature is an average. Okay, it's not saying that every single molecule is moving at a certain speed. It's talking about the average speed at which they're moving. And we use our thermometer. And so we can draw the molecules with little tiny arrows bouncing around slowly, or big arrows imply that it's bouncing around quickly. More collisions, right? We're going to be seeing it hit that thermometer more. We're going to get a higher temperature reading. When it comes to temperature, we have several different units we can use. Fahrenheit is obnoxious. We don't use Fahrenheit. It's useless, okay? Celsius is usually what we use, and then sometimes we use kelvins. Remember from the gas law chapter that 0 Kelvin means there's no motion. 0 really means 0. It's an absolute temperature scale. We use it when we're worried about getting negative numbers. When that's something we don't want, we use kelvins. Sometimes you can use Celsius if it doesn't matter. I love this picture because I think it shows why we prefer Celsius and Kelvin. If you look here, at 0 Celsius, water freezes. That's how they came up with what 0 Celsius was, right? At 100, it boils. That's a nice increment, right? 0 to 100, that's a nice chunk of numbers to deal with. Versus 32 and 212, that's pretty random. When you look at Kelvin compared to Celsius, can you see that the size of a degree is the same? The amount of temperature change between a Kelvin and a Celsius is identical, but the amount of temperature change between a degree Fahrenheit and a degree Celsius is not the same. The Fahrenheits are much smaller increments. So the reason we can easily convert back and forth from Celsius and Kelvin is really all we have to do is shift our numbers. We don't have to use a weird equation with fractions and stuff like we do when we convert with Fahrenheit. Because these are the same size increments, all we have to do is shift our numbers. We just shift our thermometer. So whenever you're taking a difference and you're subtracting kelvins or you're subtracting Celsius, it actually ends up with the same answer, which is kind of nice. I like this graphic too. Just shows you at 0 Kelvin, what would our Celsius and Fahrenheit temperatures be? What temperature do things freeze at? What's our body temp? And then all the way up here, water boiling. Okay. The big reason we like kelvins, like I said, is that we don't end up with negative values. If we're trying to measure the motion of molecules, a negative number does not make a lot of conceptual sense. To convert back and forth between Celsius and Kelvin, you add 273, or if you're going the other way, you subtract 273. Yes, there's some decimals there, but we don't really care. It's good enough to just use 273. If it ever mattered, I would tell you what to use, okay? One of the reasons we don't really care that much is because our thermometers are never that good. And so if you say 273, you'll be plenty good enough. I think it's real interesting that we've never gotten to absolute zero. We've gotten very, very close, but not all the way. people don't really know what would happen. At absolute zero, if there's no motion, a lot of the fundamental rules that we follow in quantum mechanics about how things like electrons behave kind of start to fall apart. And so it's a pretty complicated concept. Really, if you understand what kelvins mean and what absolute zero means, that's all I would ever ask in this level of chemistry class. Okay? All right, everybody, that's it. I hope that was helpful. Bye.